Today we're going to cover section 2.2b, so it's part 2. Today we're going to learn how to find the domain of a function. So the domain is going to be the x values of a function. So if I give you a list of ordered pairs, it's super easy. You just tell me the first number in each ordered pair. However, what we're going to be doing today is finding the domain from a function, from an equation. Now, if I give you a picture of a graph, and we won't do that today, but you would look at the points and you would read them always from left to right. So today we're just going to find it. I'm going to give you some functions and you're going to tell me what the domain is. So again, remember that domain is always the x values of the function. Now, you should always start out by thinking that your domain is always going to be all real numbers. However, there are a few exceptions to this, and that is when you have a fraction and when you have a square root. And when you have a fraction and a square root, we're going to need to figure out what numbers that we need to exclude from the all real numbers. And I'll let you guys get catch up on this, and then I'm going to talk about each one. So on this slide, it says that, again, you would start out by always thinking that as soon as you look at the function, you're going to say, oh, the domain's all real numbers. So you're going to write all of your answers for the domain in interval notation. So all real numbers is written from negative infinity to positive infinity. However, when there is a fraction, what we're going to do is set the denominator not equal to 0, and we're going to solve for x. If you have a square root in your fraction, and let's say it's in the numerator, we do not want any imaginary numbers. So we're going to be setting what's under the square root greater than or equal to 0, because we only want positive answers. And then if there's a variable under the square root that's in the denominator, we now have to use the rule that we don't want a 0 and we don't want it to be negative. So this is why we would only set the square root that's in the bottom of the fraction only greater than 0, because it can't equal 0, because then it's undefined. So let's go ahead and we're just going to do a bunch of examples of finding the domain. So here is our first example, and it's just a list of ordered pairs. So when you're given a list of ordered pairs to find the domain, all we're going to do is pull out all of the x's from each ordered pair. Because again, remember, domain is the x value. So you could put domain equals, and then you're going to write your answer in set brackets. So you would put 3, 4, 5, 8, and close the set brackets. If you want to just abbreviate domain, you could put D equals, but just write it in set brackets. All linear functions are all real numbers. So if you think about it, if I were to graph this function, if I draw a coordinate plane here, and if I put my first point on positive 1 and then I rise to run 1, my graph is going to look something like this. Notice the arrows on either end. So this means that I could come up with an x value for every single ordered pair that's on this line. So all functions that are in y equals mx plus b form, all linear, where x only has an exponent of 1, these are always all real numbers. Nothing gets excluded here. I don't have a fraction. I don't have a radical. So as long as it doesn't have a square root or a fraction, I'm not excluding anything. And everything is going to be all real numbers. Same thing on the next one. It's linear. So it's going to be all real numbers. No fractions. What I'm looking for is a variable in the bottom of a fraction. So this fraction here, this is really negative 2x over 3. When the x is behind the fraction, this isn't in the denominator. So the only time you would exclude something is when there's a variable in the bottom of your fraction. Next one, same thing. This is actually the graph of a parabola. Okay, again, no fractions, no radicals here. So this one is also all real numbers. If I were to graph this, it's going to take on a U shape, and it would look something like this. Eventually, this U is going to get wider and wider, and it would cover the entire x-axis. So that's why this one is all real numbers. Same thing with the graph of the cube function. So if I were to graph this one, notice there's no radicals and no fractions. The graph of the x to the third power looks something like this. And eventually it would keep covering the entire x-axis. So this one is also all real numbers. So when in doubt, I would guess all real numbers. But the only time that it's not all real numbers is when you have a fraction and there's a variable in the bottom, and when you have a square root. So here is our first exception to the all real numbers. Remember, when you have a fraction, we will take the denominator and we are going to set what that variable that's in the bottom, or the whole denominator, not equal to 0. So for this function, the domain is all real numbers except when x equals 0, because then it's undefined. I can't have a 0 in the bottom. Now, I'm not going to write my answer like this. I'm going to write my answer in interval notation. So let's get a visual, and let's think of this as a number line. So if I have my number line here, and here's 0, 0 is where there's a hole, but then it's all the other numbers. So over here is negative infinity, positive infinity. And the way that I'm going to write this in interval notation is I'm going to go from negative infinity up to the 0. It's got a parenthesis around it. Then I jump over the hole and put a U, and then I start up again at 0 and go to infinity. So it's coming along here left to right, jumping over the hole, and then I keep going around that. So you would only put brackets if it were greater than or equal to. And it can't include 0, so that's why it's not a bracket. Let's try the next one. Again, I want to take a look. Again, always start out by thinking, oh, it's all real numbers. Oh, but wait, it's a fraction. I got to figure out what I need to throw away. So x cannot equal, set that denominator, not equal to 0. So x cannot be positive 5. If it is, it makes the denominator a 0. So again, if you want to see it on your number line, where the 5 is a hole, but then it's everything else. So this would be from negative infinity up to the 5. It comes along here, hits that 5, jumps over it, and then it keeps going. So the hole is the U, and then it starts up again on the other side of 5, and then it keeps going to infinity. Same thing on number 8. I've got a variable in the denominator, so I need to set the denominator not equal to 0. So 2x plus 1 cannot equal 0. Move the 1. Divide by 2. X cannot equal negative 1/2. So let me go ahead and I'll write the interval notation up top here. So again, if you put the negative 1/2 here, that's where the hole is, and then it goes that way. So negative infinity up to the negative 1/2, unioned with negative infinity to infinity. All parentheses.
Miss Corey?
Yes. Yep, only check denominators, not numerators. The only time we check the numerator is when there's a radical in the numerator. And we're going to see that coming up. All right, let's try number 9. Still fractions here. We're still testing just fractions. So again, I'm going to take my denominator, set it not equal to 0. Now I can either factor this or do the square root method. Either way, we could do the square root method. I know with the other class I was factoring it. Either way, when I square root this, x cannot equal plus and minus 1. So let's put this one. This one's a little bit more complicated. So let's go ahead and draw the number line so we have a visual. I'm going to put -1 here, +1 here. Remember, that's where my holes are located. X cannot be these numbers, but it's everything else. So I'm going to have 3 different things here. So, -infinity to -1, then it jumps over it, and then now it's filling in this section, which will go from -1 to 1, then it jumps over that, and now we'll do this section, and it goes from 1 to infinity. So this would be this section. And those parentheses mean that it's just like the cutoff point. It doesn't include them. Now, when we're doing this domain, we're only looking for real numbers. We're not looking for any imaginary. So if when I set my denominator not equal to 0, if I end up with an imaginary solution, that's nothing that I'm trying to exclude. I'm only graphing real solutions here. So on the next one, number 10, when I go to try to set my denominator not equal to 0, and if I move the 4 over, I get x squared not equal to -4, square root it, and I get x not equal to plus and minus 2i. This is an imaginary solution, so nothing gets excluded. So this answer is going to be all real numbers. I'm not worried about excluding imaginary. We will not graph imaginary in this class. Okay, so now for number 11, now we're starting the test for the square roots. Remember, because I only want real solutions, I don't want a negative number under the square root. So this is why we're going to take what's under the square root and we're going to set it greater than or equal to 0, because that will give me a positive answer. So now for this one, remember it can't be negative, that's why I put it like this. So on my number line, this would be either a closed circle, you could either think of it as closed going this way, or a bracket going this way, either way. So in interval notation, this would be from 0 with a bracket, because it's greater than or equal to, and then to infinity. Can't be any negative numbers. Let's try number 12. Same thing, it's just a square root. The square root's not in the denominator yet. So we would set it greater than or equal to 0. Solve this for x. X must be greater than or equal to 3. So again, if you wanted to see a visual here, put the 3, closed circle going this way, or graph it with the bracket. So here it's going to be, the answer will be 3, comma infinity, and the 3 gets a bracket. So it's all numbers 3 or bigger. Still radicals. So again, take what's under the square root, make it greater than or equal to 0, add the 1, to x is greater than or equal to 1, divide by 2, and x has to be greater than or equal to 1/2. So again, put your 1/2, close circle, going to infinity. So 1/2 with the bracket, comma, infinity with the parentheses. Next one, same thing, but just be careful because that variable is negative. So watch what happens on this one. Again, take what's under here, greater than or equal to. I'm going to go ahead and add the x to the other side. You could subtract the 4 and then divide by -1. Notice Mr. Alligator here is eating the 4, so if I flip this around, now it's all values that are less than or equal to 4. So this would be a closed circle going to negative infinity because it's less than. So this would be negative infinity with the parentheses, comma 4 with a bracket. Because I moved it around, my inequality symbol reversed. 15, now we're moving the radical to the denominator. Remember, for the denominator, we don't want it to be 0, and because it's a radical, we want it to be positive. So when the square root's in the denominator, you take what's under it, but this time it's only greater than 0, because it cannot equal 0 when it's in the bottom of a fraction. And so then graphically, this would just be an open circle going to the right. So this would be 0, comma, infinity, and they're both in parentheses. Next one, same thing. There's a square root in the denominator. Make it greater than 0. Add 1. Divide by 2. So x has to be greater than 1/2. So 1/2, comma, infinity, both in parentheses. Now we're going to combine everything. And more than likely, examples 17, 18, 19, and then the 2 that I'm going to add will probably be more likely what you would get on the test. Okay, where they're combining all the different exceptions. All right, so now we got a fraction. Oh, we got double radicals here. So I need to check both. My domain is only going to be the solution to both, where both of them are graphed together. And you're going to see this. I'm going to do it in different colors. So let me go ahead and do the numerator. I'm going to take the x minus 1 that's under the square root. Whenever your square root is in the numerator or just all by itself, it's always greater than or equal to 0. However, when the square root's in the bottom of the fraction, remember this is only going to be greater than 0. So when the root is in the bottom, the radical in the bottom, it's only greater than 0. Now I need to solve each one individually. So I'll add 1. X is greater than or equal to 1. And then this one I'll subtract 2. And x is greater than -2. I'm now going to graph both of these on the same number line. I'm going to put it in here least to greatest, so the -2 first. Actually, let's do this so I can distinguish the colors. All right, so I'm going to graph this one first in red. So it'll be a closed circle on +1 going to infinity. Then I'll graph the blue one. This will be an open circle on -2, again going to infinity. Now, the numbers that need to be excluded is where the line is both red and blue. So my domain can only be from +1 to infinity with a bracket because it was a closed circle. So it's got to be where both are. So when you have two things to check, you need to graph it or see where they're both in common. Let's try the next one. I only include the domain where it's a solution for both. So it has to be where the red and the blue line are both starting out at. So that's why I only start at the 1, because this section here will not be satisfied for the numerator. It would make it negative. So that's why I only start my domain from where both lines are together. Again, I've got a fraction and I've got double radicals here. I need to check both. So I'm going to take my numerator. And again, remember, for the numerator, when the radical's in the top, it's just greater than or equal to 0. But for the denominator, we can't have it equal 0. So that's why it's x plus 3 greater than 0. Solve each one. 2x equals 1. Divide by 2. X is greater than or equal to 1/2. Do the same thing for the blue. Subtract 3. And x has to be greater than -3. So let me go ahead and get this on my number line. Put the -3 over here, the positive 1/2 here. I'll graph the red one first. So this will be a closed circle on 1/2. This will be an open circle on -3. And again, I only start my domain where both lines are. So this would be from 1/2 to infinity, and 1/2 is a bracket. Now the next one's a little tricky. Well, maybe not so much. No, it's not bad. All right, let's try the next one. We actually have to factor it or do the square root method, either way. So again, I've got a radical in the numerator. So I'm going to take what's underneath the square root, make it greater than or equal to 0. Take the denominator, what's under the square root, make it only greater than 0. So I'll solve the red one. X has to be greater than or equal to 1. Over here I can do the square root method, or I could factor it. I could make it x plus 9, x minus 9. You might be more inclined if you factor it and then you don't forget about the positive negative. Sometimes when you move it to the other side and you square root it, some people would only put 9 as an answer. So then this would give me x has to be greater than 9 and x has to be greater than -9. So now I have 3 things to put on my number line. -9, 1, and 9. So let me graph each one. So I'll do the red one. Closed circle on +1, going to the right towards infinity. Then I'll do this one in blue. Open circle here, going here. And then now lastly, I'll do this one in green. Open circle over here, going here. So again, this time, instead of just where red and blue are, I want where red, blue, and green, all of them are. So from this point here, and then going to the right, again though, the starting point has got an open circle, so it'll be a parentheses, 9 to infinity, because of that open circle on the +9. Now I'm going to add 2 more examples. Good chance that something very similar to these will be on your test, so I would pay close attention. Everybody ready? Let's see, what time is it? We got lots of time. Everybody ready? Stretch. Here we go. Now add a blank page. All right, so we have x minus 1 under the square root over x squared minus 9. No square root in the bottom this time. So for the numerator, it needs to be positive, greater than or equal to 0. For the denominator, no radical here, so just not equal to 0. So now let's solve them. Add 1. X has to be greater than or equal to 1. Over here, you can either move the 9 and do the square root method or factor it, either way. If you factored it, it was this. Set each of these factors not equal to 0. So x cannot equal negative 3 and x cannot equal positive 3. So now let me add this to my number line, just so I get a visual of what it's going to include. So generally it's the entire number line, except for these exceptions. So I have negative 3 here, 1, and positive 3. So at both negative 3, it's a whole. We can't include that. Over here at positive 3, it's a whole. I can't include that. And then for this one, oops, I don't want to color on top of it. It's going to be a closed circle on 1 going to infinity. Now, for this one, what I need to do is my domain is going to be everything that's greater than 1 except the whole of 3. I don't need to worry about this because that's a whole there. So really there's nothing to the left of positive 1. So I'm going to go ahead and write this from 1 to 3. So it's this section here. But then I have the whole, and then I jump over it, start again, and go to infinity. Let's try one more. One. We're going to do x minus 1 under the square root again, and this time just an x in the bottom. So again, when you have a radical in the numerator, take what's underneath there, make it greater than or equal to 0. And then for the denominator, no radical, so it just can't equal 0. So then here I'm going to solve. Add 1. X has to be greater than or equal to 1. And x can't equal 0. So again, give yourself a visual. So get your number line here. Put the 0, put the 1. And then for this one, close circle on positive 1, going to the left. And then here, just an open circle on 0. Well, that open circle means that you can't include it. So I'm just writing my answer from 1 to infinity with a bracket. So that one wasn't that bad. Ask how come everything less than 1 was taken out, because that's what we got from setting the numerator to be greater than or equal to 1 or to 0. So over here, this blue circle right here means that you can't include 0. Well, we never had anything over here in this section for our domain, so it really didn't matter. So our domain is only starting from this point and going to infinity. Okay, so he said, what if x is not less than or not equal to 2? So let's make a new problem. Let's do x minus 1 under the radical, and then x minus 2 in the bottom. So again, I would take my numerator, set it greater than or equal to 0, and the denominator would be x cannot equal 0, or x minus 2 can't equal 0. So here I would add 1, and get x has to be greater than or equal to 1. Over here, add 2, so x can't equal 2. So let's go ahead and put this on our number line. So I'll do this one in red. So I'm going to add the numbers 1 and 2 on here. So this one would be a closed circle in red, going this way. But this one would be just a hole here. So what we would do when we write our domain, it would be from 1 to 2 with a parentheses. So it would come along here, jump over the hole, and then keep going. So union 2 to infinity.
So if there was a -2 behind the 1, would we not include that when we write it?
Correct.
Okay.
Pretty good? All right, so that is it for finding domain. I will be adding a WebAssign assignment